Hello, geometry students, and welcome to the continuing series of videos on circles and tangents of circles in particular. And in this video, I am going to explain Theorem 10.1 as well as prove one part of it. So it says here, in a plane, a line is tangent to a circle. And remember, this tangent to a circle means that it touches the circle exactly once. Okay. If and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So if and only if here means that there's really two parts to the theorem. So part 1 of Theorem 10.1. So I'm going to start out with a picture here. Here's my picture. And let's say this is Q, this is line L, okay, and let's say this is P. Okay. So part 1 is saying that if I'm going to name some other point here, let's say W. If line PW is perpendicular to PQ, then PW is a tangent of circle Q. Okay. And the other direction is, of course, saying that if PW is a tangent of circle Q, then PW is perpendicular to PQ. Okay, I forgot to make this mark here. Okay, so both directions of this are true. If it's perpendicular, then it's a tangent, and if it's a tangent, then it's perpendicular. Okay, and I am going to prove the first part of this because it's a little bit more difficult and it presents kind of a more interesting proof technique. Okay, so I'm going to prove the first part of the theorem that says if PW is perpendicular to PQ, in other words, this is a radius, then PW is a tangent of circle Q. In other words, PW touches the circle only once. I'll use the more technical term, intersects the circle only once. Okay. And what I'm going to do with this proof is I am going to prove by contradiction. Okay. And this is a new proof technique. So what we're going to start out doing is assuming the opposite of what we want to prove. So this says PW intersects the circle only once. I am going to make an assumption. I'm going to assume that PW intersects the circle twice. Okay, I can say 3 times, 4 times, but proving this is using this proof for 2 times for 2 intersections is good enough, and we can replicate it a bunch of other times. So let's say that it intersects the circle twice at P and at some other point. Let's call this, I don't know, A. Okay. There we have it. Okay. Now let's see. We're going to work through this and eventually arrive at a contradiction. So now what I'm going to do next is just connect these lines here. Okay. So construct AQ, PQ, and AP. So if we do that construction, you see that this makes a triangle. So A, P, and Q form a triangle. Now, if you look more carefully at the triangle, there's something rather unusual about it. And let's get there a little bit at a time. So you can see here that PQ has a distance of R because it's the radius. Okay, and AQ also has a distance of R because that's also the radius. So these 2 line segments here are congruent. So I'm going to say triangle APQ is isosceles because AQ and PQ are both radii of the same circle. But that leads us to kind of a big problem. So I'm gonna draw the triangle down here just so we can see it a little bit better without the circle. So from this image up here, we have a 90-degree angle outside. So that means the angle in here is also 90 degrees. That means this angle is 90 degrees. But since this is an isosceles triangle, this angle is also 90. Angle A is also 90 degrees. Okay, so I'm going to say the measure, or A, is congruent to angle P. So that means this is base angles theorem. That means the measure of angle A is equal to the measure of angle P, which was equal to 90 degrees, and that was given. Okay, it was given that it was 90 degrees. Okay, but this is a huge problem because you have a triangle with two 90-degree angles. So that's a contradiction, because you have an impossible triangle with two right angles. Okay. So what we can conclude here, therefore, statement 1 is wrong. The assumption in statement 1 is wrong. It's definitely wrong, because if it was right, it would lead us to having an impossible triangle. So that means if this assumption is wrong, then the opposite of the assumption, which is what we tried to prove here, must be correct. Okay. So this is kind of a weird way to approach things, but this is basically saying I want to show that something is true, so I'm going to pretend the opposite of it is true, and then show that the opposite of it leads to a contradiction. Therefore, the original statement must have been true. Well, and again, this is kind of a tough proof, but it's a nifty and very useful proof techniques in a lot of more difficult situations and more difficult problems. It takes a while to get the hang of it, so if you kind of have a hard time understanding, always ask your teacher for help. Thank you for watching, and have a wonderful day.